Hey! Welcome to Tech News Station. Today we'll talk about building high-rises out of wood can help save the planet. So let's begin. The modern industrial era was literally built on steel and concrete, readily available materials that gave buildings the strength to stretch hundreds of stories into the sky. Unlike wood, steel and concrete don't catch fire from a mere dropped lantern. Soon, city-razing conflagrations, like those of San Francisco in 1906 and Chicago in 1871, were a thing of the past, at least until climate change began supercharging wildfires in California. Poor old wood had been relegated to smaller buildings like homes until environmental scientists started raising their voices about something everyone was overlooking: manufacturing steel and concrete pumps massive amounts of carbon into the atmosphere, both in terms of the energy it takes to make the stuff, and the CO2 that spews from chemical reactions as the materials form. Wood, on the other hand, actually captures carbon, at least during the time when it's part of a living tree, as a tree's leaves suck in CO2 during photosynthesis. Once trapped inside the wood, all that carbon stays out of the atmosphere. As our planet continues to spiral into a climate catastrophe, architects have in recent years taken notice to wood's virtues, including its merit as an extra strong composite material, and have been honing their skills building high-rises up to 275 feet tall out of lumber, leveraging newfangled wooden materials. These are no giant log cabins. And today, writing in the journal Nature Sustainability, a team of environmental scientists and architects have quantified just how powerful wooden urban buildings could be in mitigating climate change. For the first time, we're able to show that at the global scale, this strategy really makes sense, says lead author Galina Cherkina, an environmental scientist at Yale University. We were able to quantify emissions and carbon storage, and we were also able to show that there is enough wood for the transition to timber cities. The study's authors found that if living standards continue to rise and people demand more space, and we keep constructing buildings from concrete and steel, the associated emissions could reach 600 million tons a year by 2050. But construction of timber buildings for new urban dwellers could store up to 680 million tons of carbon a year. The more timber structures we build, the more carbon we keep sequestered, plus skipping the steel and concrete manufacturing keeps even more carbon out of the atmosphere. To get these figures, the researchers did a whole lot of scaling up. They used accepted figures for the emissions involved in making a ton of steel or concrete, and the emissions you'd sequester by producing a ton of timber. Then they scaled that up to how much material you'd need for a building, then scaled it up to how many materials you'd need per capita to build new structures. The team accounted for population growth, as well as the increasing demand for space as people around the world ascend into the middle and upper classes. This transition is feasible under two conditions: that the harvested forests are sustainably managed, and that the carbon that is transferred from forests into the cities and stored in the buildings is preserved in some form after demolition of buildings, says Cherkina. That is, we can't just go chopping down forests willy-nilly, and we can't just burn the buildings after we tear them down. That'd just put the carbon right back into the atmosphere. Instead, that wood needs to be recycled, for instance as floorboards in new homes. Now, we're not just talking about cobbling together a 20-story building out of mere 2x4s. Modern timber high-rises make use of cross-laminated timber, essentially large-scale plywood, made by gluing 2x4s together into a sheet, then flipping the sheet 90 degrees and gluing still more 2x4s on top. You end up with basically a sheet of wood that is in its size, and the way you use it when you engineer or design with it, very similar to a slab of concrete, says Michael Ramage, director of the Center for Natural Material Innovation at the University of Cambridge, who wasn't involved in this new work. It just weighs 1/5 the amount. Keep that weight factor in mind, it'll be important later when we talk safety. As an analog for steel, architects also use glue-laminated timber. It's the same principle, only the end product is beams instead of sheets. These can support a structure, and architects can even bend them to craft flourishes like domes. The beauty of both cross-laminated and glue-laminated timber is that they leverage the pound-for-pound strength of wood while getting rid of some of its organic weaknesses. In the manufacturing process, each component piece of timber is scanned for imperfections that could weaken the material like knots, which are cut out before the pieces are glued together. In the last couple of decades, the manufacture of these kinds of composites has, ironically, turned an ancient building material into what's really the only new structural material in the last century, says Ramage. You have to go back to basically reinforced concrete and emergence of structural steel, both at the end of the 19th century, for a new structural material at the scale of buildings. Before moving forward, subscribe Tech News Station and press bell icon for more updates about latest tech news. Still, these newfangled materials inherently limit the scale of wooden buildings. A 10-story steel building weighs 2 or 3 times as much as a wooden version. Because of that, as you get higher, wooden buildings counterintuitively have to be stiffer than steel or concrete, says Ramage. This is your fault as a human, really. Buildings have to sway in the wind or earthquakes so they fail, but they can't sway too quickly, or they'll make their occupants seasick. Because wooden buildings are so much lighter than ones made of steel and concrete, they move much faster in the wind. It's not even the amount of movement, it's the speed of movement that we're susceptible to, Ramage adds. It's like being on the rocking deck of a ship. Accordingly, architects have to design these lighter wooden buildings to be stiffer than traditional skyscrapers, but not too stiff, or they'll fail in the wind. That limits how high they can go. But there's an upside, because timber buildings are made of lighter stuff, workers can assemble them faster, saving the client money. The cost of the laminated materials remains high, but prices are coming down. They don't have to weld steel beams and pour concrete. We can't talk about wood without talking about fire. Sure, fire can burn thinner sections of the stuff, but thick pieces of timber tend to only char, not burn to the core. Consider a log in the fireplace that doesn't have enough kindling to really catch. And architects point out any building material comes with its vulnerabilities. Steel is vulnerable to fire, so we wrap it with sheetrock or other non-combustible materials, says Alan Organshee, of the Yale School of Architecture and the firm Gray Organshee Architecture, co-author on the new paper. Concrete is superconductive thermally, so we have to insulate around it to keep cold and heat from being conducted through the material. The more architects explore these fancy new timber materials, the better they're getting at designing elaborate wooden structures that double as carbon-sequestering living spaces, seeing the forest for the trees, and then some. Don't forget to like the video. Hope to see you guys again.